Well, hello class, guys. How are you doing? I could be watching all those videos all day. So, we start, we left, let me admit one more. And we left last class talking about standard deviation. Do you remember that formula? So let me start sharing my screen. Homework. And I did talk about sending you guys some homework, but I thought I'll wait a little bit. I'll compile a homework for you. That way you could practice. Can you see my screen? Just want to make sure that you guys are seeing my same screen. Okay, good.
Yes, we're able to.
Good. I got a message from Emily. Good. Okay, so we're gonna start. This will be our last class for statistics, and then I want to move on to a workshop that our good friend David Bernard is gonna give out on 3D. And so the next class, I want to give you kind of like a little background before the workshop to talk about what's 3D. And I know like some of you guys are interested in, because 3D it covers a lot, but I would like you to, as well as statistics, teach you the basics, and then that way you could start learning it from now. So this will be our last class on statistics, and then we'll move to 3D, and then we'll go back again to probability. Kind of like use statistics to find the probability of an event happening. So last class we talked about, there were like 3 ways. Once we get our sample data or population, then we're gonna have some variation between our data, and just the variation was how the data was spread. So we did talk about having 3 ways. We talked last class about the first one, which was the maximum minus the minimum, but it was only taking in considerations 2 numbers, and it didn't give us a lot of information. And then we talk about our perfect formula standard deviation, which you're gonna use it a lot in statistics, and it's very important, and basically was how far our data points were away from the mean. And we're gonna have one for our sample, and we're gonna have one for our population. You guys remember those, or will you like me to just go over them just really quick? Well, I have it here, so I'm just gonna go over them pretty quick. So we said that this was our formula. Can you see it? So we said our sample data subtracting away, like how far were they from the mean. So we subtract from the mean, that way we'll get how far. And since we're gonna have positives or negatives, we kind of like raise it to the square, and then we take the square root of the whole result. And we did subtract a -1 because it's a sample, but we don't do that for our population. Remember that? So we use a big letter N, and we use a -1 to overcompensate our sample. So you remember this symbol? On our population, we use sigma, which is kind of like a circle with a line, and then we use the mu instead of mean. And then on sample, we use X bar, and we use S. Do we need a pen and paper? It's always good to have a pen and paper. I would say yes, we need a pen and paper, but we don't need, we're gonna need pen, paper, and a calculator if you have one available. Last class we did this, was a lot of mathematical equations. They weren't hard. They were just kind of like step 1, step 2, getting the mean and just subtracting each one. So today we're gonna learn the empirical rule. So this will be our last way to get the variation. So the empirical rule talks about having a normal distributed data set. That's always the key. So whenever we have a data that's normally distributed, do you remember how does the bell curve look like, or how does the shape of the curve looks? So we said we could look skew to the right, skew to the left, or let's do that. Or it could look like this. I'm getting good at those. So this means that it's normal. What's in the center? On the center, let's suppose this one, it's a sample. So in order to be normally distributed, what's at the very center? If it's a sample. So we said in order to be a normal distributed, it's gonna be our average, which is mean, will be equal to median, will be equal to mode. So what's the symbol of mean on our sample? Yeah, very good, mean. So X bar. So that's the mean of our sample. So this is gonna be our X bar. Okay, so we're gonna continue. And then we're gonna have some percentage. We're gonna have 68, 95, and 99.7. So what does those, well, I'm gonna come back to the homework. What does those percentage means? So basically the empirical rule, it's comparing a percent. So we have the mean on the center, and it's comparing a percent to the left and a percent to the right. So that's why we have these three percentages. The 68, 95, and 99.7. I'm gonna explain them further. So I was thinking about having a little homework on the normally distributed, but I think I'm gonna send that to you guys. That way we'll continue with the empirical data. So we said in order to have a standard deviation, if it was small standard deviation, if it's small, that means it's close to the mean. That means we have a very close group. If it's a large standard deviation, so meaning you're gonna have more data over here, your data is gonna be more spread out, depending on our standard deviation. So let's see. So this is gonna be one standard deviation, and this is gonna be -1 standard deviation. Let's go, -1. What was the symbol for standard deviation for a sample? Let me think. S, very good, very good, yes. So over here, it could be 1S, And over here it could be minus 2x. I mean minus 1x. And then over here we're gonna have plus 2s, 2 standard deviations. And over here minus 2s. And then it's gonna be 3s minus 3s. And this is only gonna work with normal distributed data. So we said that it could be skewed to the left, skewed to the right, or what we wanna accomplish is always normal distributed. That's what we said. Mean, median, mode will be at the very center. So the empirical rule is basically, it's gonna compare percentage-wise, compare it to the mean. But you'll see why this is important. So 68% of our data will fall between 1 standard deviation of the mean. So we said that this is 1 standard deviation. So let me color it pink. So if our data is normal distributed, what percentage will be of our data here? 68, very good. So we're gonna put here 68. And this is called the empirical rule. So it's a rule. So if it's a normal distributed, 68% of your data will always fall between 1 standard deviation, even if it's a sample or if it's a population. It doesn't matter as long as it's normally distributed. And then we have so I had here an example. So if you divide this 68% divided into 2, so over here, half of them will be 34%, and then over here will be another 34%. And together there are 68. Plus 1 standard deviation, minus 1 standard deviation. So first we get our average, and second we get our standard deviation. And then second standard deviation will be like 95% of our data will fall between 2 standard deviations. So I'm gonna use a green. So that means between here and here, all of this how much data will be in all of our green? All of our green. 95, very good. So from here till here, all of this is 95. And that will be 2 standard deviations. So 2 standard deviation inside is 95% of our data. $34, and then from here to here, 13.5, and then over here will be another 13.5. So if we add 13.5 plus 34 plus 34 plus 13.5, it will give us our 95%. Very good. And then at the end, we're gonna have our 3 standard deviations. So this is not only covering this, it's covering our whole so all this from here to here. How much is it? 68, 95. What's our last percentage? 99.7. Very good. And whenever you have like large amount of data, like thousands of thousands, will you ever get 100? It's very rarely, right? Yeah, it's very rarely that you're gonna be able to count all 100%, unless it's a very small set of data, like our families that we count. Remember, we count like the ages of our family, and we didn't got a normal distributed. It was kind of like spike, like or skew. So it's really difficult to get 100%. You're always gonna have that. You get to 99.7, 99.9, 99.999. So we always, if it's under between -3 standard deviation and +3 standard deviation, is 99.7. So and I want you to clarify also, whenever you get a data point, we're gonna go through some exercises, but if it's between 1 and 2 standard deviation, it's pretty usual. Like, it's pretty usual. But after 2 standard deviation like this, it's very unusual that you get somewhere over here. You'll get it, but whenever they ask you if it's very usual, like most of your data will be between 95%, which is between 1 and 2 standard deviation up or down. So I got this point from here to here, 0.15%. And then over here, another 0.15% of the data falls between that, between this space. So far, so good. I wanted you guys to understand, what does it mean 2.35? Where 2.35? Is this a 2 point here? On the graph on the screen. Oh, 2.35. Oh, the 2.35, that should be here. So 0.15, so if we add 13.5 plus 34 plus 34 plus 13.5, and then over here, it's gonna be 2.35. not 0.15. The 0.15 should be here. 0.15%. Oh, that was my mistake. 2.35. And then this will be 0.15 and then 2.35%. So let's see, someone at 2.35 plus 13.5 plus 34 plus 34 plus 13.5 plus 2.35. We should get 99.7. Is that right? And then the 0.15 will be adding 0.15 and 0.50 will be 0.3. So that will be the rest of this. Yes, ma'am. Okay, correct. Good. Thank you. So what I want you to understand with this graph is whenever, so remember on here, we got our standard deviation, our letter S, or our letter sigma, depending on if it was our sample population. So what I want you to understand with that is once we got our letter S, this will be our letter S. So you plug in here the number that you got. So here will be one standard deviation. So 1 times whatever number. I think on this example, we got 7 or S, and over here was 1.73. So once you get your standard deviation, you're gonna be able to plug it in here and say, okay, the mean or whatever sample data you have, or if you wanna say, okay, if we got this number, does it fall between 1 standard deviation, 2 standard deviation, or 3 standard deviations? So if you got a number that, you say you're measuring a hole and your hole is bigger than usual, does it like usual, or is very unusual what we got? Remember what we talk about outliers? If it's an outlier, it should be way over here because it's skewing your data. It's not usually between your regular 1 or 2 standard deviation. So if the data value lies between, that's what I was kind of like explaining, it's considered usual. But if it falls outside your 2 standard deviation, will be unusual. So let's do an example. Let's say, that way you get this idea better. So if we have a mean of 65, do me a favor, do you all have a piece of paper and a pen? Cool. Will you be able to draw what I got here, kind of like a nice curve or like a nice bell shaped curve? And I'll do it on here too. And then we're gonna, once you're ready, let me know, and then we'll attack the sample problem. For this one, we use the X bar answer or the sample. The X, this is a sample. I think I'll do it with you. I mean, with you guys. Let's do it together. And I just want to make sure that you guys already draw the curve. So what does it mean? X bar. X bar will be the mean of the, if we're talking about a sample. If we're talking about a sample, we use X bar. If we're talking about population, we use this letter called mu. That will be the mean of the population, and X bar the mean of the sample. So first we need to know, that's very good. First we need to know, are we talking about a sample or are we talking about a population? So in this example, we're talking about a sample. So we're gonna talk about a sample. We're gonna use our sample variables, which is X bar, little letter N, total samples, and it will be the same, total samples. So say that we already had our standard deviation. So we already had our standard deviation, and our standard deviation was 3. Okay, you guys ready? I'll wait a couple more minutes, maybe 1 more minute. But where we can find S. So S is gonna be given, it's given on the example, whenever it says example with a mean of 65 inches. So let's start. If we have a mean, that means we're talking about a sample and our mean will be X bar, and it's 65 inches, right? And then we have a standard deviation of 3. So we're gonna start with 1S, and then we're gonna have 2S, and then we're gonna have 3S. And then over here, we're gonna have minus 1S, minus 2S, and then minus 3S. Follow me? And then since it's didn't catch this word, where we find S. S is given to you. On this example, it's given to you. But if you didn't had standard deviation and they just gave you some sample data, then this is the formula that you will use to get it. But in this case, they give it to us. So it says on the example, with a mean of 65 inches and a standard deviation of 3 inches. So a standard deviation will be 3. So let's see. So in this example, S, which is our standard deviation, S, it's equal to 3 inches. X bar, it's equal to 65. And since we're talking about a sample, we're going to use X bar and S, and it's normally distributed. Normally distributed. Let's see. Okay. Sorry, Zach. We kind of like, sorry, Zach. You were in the waiting room. And I don't know for how long. I hope not that very long. So, okay. What about N? So N is the number of, the N, it will be the number of, so N It's the number of total samples. So right now, in order to make it simple, we don't have how many samples. We only have standard deviation. So we already have the S. S will be equal to 3. Because I wanted to show you what does this mean. So if we got a mean of 65, and then we have a standard deviation of 3 inches. So if we got, so over here will be 1 times S. So what's S? 3, right? So we got 1 times 3 will be plus 3. 1 times 3 is 3. Plus 65 over here will be 68 inches. So that will be 2S. 2 times S, which is 3 inches, will be 6 inches. Plus 65. Will we ever need to find S base of the mean and the standard deviation? No. As in working backwards for the equation S. I have not seen a problem like that in statistics. I bet if you have all the data, you might be able to find it, but I don't think that's the way it's supposed to work. I think once you have your mean and your standard deviation, you're gonna probably get more difficult problems like with probability, but I don't think you're gonna need to find out the letter N. Let's see. But but it depends. You might be able to find it. So if you got your mean and you got, this will be unknown, and then you got your standard deviation, you're gonna be missing your data point.
Illusion.
Right? I don't know. That's a good question. I'm gonna find out. But for now, this is what I wanted to show you. So what I wanted to show you is like standard deviation means like it's adding up. So if I ask you a question, what will be 67 inches high? Will that be between 1 standard deviation, or how much percentage of that? How much percentage will show? So that's what I wanted to show you. That's the empirical rule. So what from like we're seeing. So over here, can someone tell me if we add 65 as our mean, and then we have 2 standard deviations up, what would be the total height here? So we said 2 times S, which S is 3. 2 times 3 will be 6, plus 65, 71. Very good. So 71. And then what about 3 standard deviation? 65, 74. And then if I ask you, will 74 inches or above it, or 73, will that be a usual data or an unusual data according to this information that we got? Do you remember that? Like if it falls between 2 standard deviation, it's usual, but if it's above it, will be unusual. So let's continue this graph. So if we have -1 standard deviation, what will be here? 62, very good. 62 inches. And then what about -2 standard deviation? 59. And then the third one? 56, very good. I'm getting a lot of answers, very good. Okay, let's continue. So if we said against, if between this information, between 62 and 68 inches, that's 68%. And then between 71 and 59, that's how much? How much percentage will fall between 59 and 71 inches? 95, very good. So between here and here will be 95% of like our data. This is the percent. What about 56 and 74? Will be almost oral data, right? Very good, Liz. 99.7. 99.7. So I got another example. So we have an example that weight is normally distributed, right? We always need to, they always need to specify that it's normally distributed in order for us to take the standard deviation, the empirical rule. To use statistics, most of the time we need a sample that is normally distributed or a population that is normally distributed. And then they're asking us, what percent of data will fall between 10 pounds and 59 pounds if we got a mean of 34 pounds with standard deviation of 8? So they're telling us like it's a sample or it's a population. Well, it's a sample again because we have our X bar at the bottom. So they're telling us our X bar will be what, 34 pounds? 34 pounds. And they're giving standard deviation of 8. So this will be another example. So we have our X bar will be 34 pounds. And our S, it's equal to 8. Normal distributed. It's gonna be example 2. And this will be example 1. So they're giving us a 34 pounds. And then what percent of data will fall between 10 pounds and 59 pounds? So what will be our number here? If they're saying that they're normal distributed, our standard deviation will be 8. What will be here? So we got 1 times standard deviation. Our standard deviation will be 8. So will be 1 times 8 plus 34. $42, very good. 42 pounds, and then 50. Thank you, Vanessa. And then 58. 58 pounds. What about over here? 26 pounds. 18 pounds. And 10 pounds. So if they're asking us what percent of data will fall between 10 pounds and 59 pounds, How much? Or 58 pounds. Let's say 58 because it's like 10 pounds to 58. I think that was a typo. 99.7. Very good. So you see this will be our blue because it's covering up to 3 standard deviations. So this will continue. This will continue, and same here to infinite. Will continue, and then this will continue. But most of our data is here, or 68, or however. But let me ask you something. I want you to clarify that even though, okay, let me do a graph here. So you got your X, and then one of them, and then you got your sample. And then your, in example 1, your standard deviation was 3. And then example 2, your standard deviation was 8, and your mean 34 pounds. And on here, 65 inches. So over here, we were talking about height. And down here, we're talking about weight. I just want you to know that even though the weight is higher, you cannot compare standard deviations because we're talking about height, and over here we're talking about weight. So they're totally different. But we're gonna learn something. I mean, they're kind of like apples and oranges. You cannot add them together. But if we compare these numbers to something called a Z-score, then we're gonna be able to relate them exactly where they are under the curve with a Z-score. A Z-score is gonna be a table, and it's gonna be a graph, and it's gonna be a table full of numbers telling you where, how do they translate. That way you compare exactly. Because right here, you're comparing weight and height only with the standard deviation, so that does not compare one to another one. Let me see if I have another example. Okay. So this is what I was telling you, like we have our weight and our height. So do you have any questions on why, so what does it mean 1 standard deviations, 2 standard deviations, 3 standard deviations, and how you get your I guess your percentage of the data when it's normally distributed. When it means normal distributed, you're gonna have this curve. Yeah, how do we get that percentage? That percentage, it's always gonna be 68, 95, and 99.5. That's always gonna be that percentage. We're always gonna have 68, and that's how it's called. So it's gonna be 68, 95, and 99.5. And what does it tells you 68? It's between 1 standard deviation. When it's 95, 2 standard deviations, and 99.7, that's most of your data, will be between 3 standard deviations. So what I was trying to explain you over here, that even though you have your mean of your sample, it will not compare. And I'll put a quick example. So for example, if you have your weight, as we said on this example, was 65, your mean, and then you weighed, let's say, was one. Did we did another example? All right. Okay, let's say your weight was 175 and then your standard deviation was 7 pounds. And then over here, same weight, but just your standard deviation was closer. So if you have your standard deviation of 0, means there's no variation, there's no deviation. So the higher your standard deviation, the broader data set you will have. We said that on the beginning. Let's see. Almost the first one. So the larger your standard deviation, meaning the larger your standard deviation, if you get a 7 of standard deviation, your data will be a lot spread out. Do you see? It'll be spread out. Like on our example, we have our standard deviation of 7. Our data was pretty spread out. We were talking about 1 and a 14. And over here, we got 4, 7, and 7. Our data wasn't that much spread out compared to 1, 3, and 14. So our S, our standard deviation was 1.73. So this 1.73, it doesn't mean like you got your standard deviation 1.73. It doesn't mean like it's here. No, it doesn't mean that your data is here. No, that's what a Z-score will do. That's what a Z-score will do. But that's kind of like when I explained, your standard deviation will only mean this S. So 1 times 1.73. So 1.73 will be right here. And then this one, which your S, it's equal to 7. You're gonna multiply this 2 times 7. 1 times 7. So your X bar over here, what's our X bar? Our X bar was 6. So 6 will be right here. And then your 1S will be 7. So over here, and then this 1, 3, and 14, they will be way over here. So our data will be very spread out because it's a standard deviation, it's a 7. So the larger the standard deviation, the more spread out it will be. So it's always gonna be 68, 95, and 99.7. The only way we can compare will be doing a coefficient of variation. What time is it? I just don't wanna, okay. We still have a couple of minutes. I still have you a couple of minutes. So coefficient of variation. Can someone help me out with a calculator and divide? So this is the formula of coefficient of variation. So it's S divided by the mean. This will be one way of comparing like apples to apples. So if we got, let's do the first one. We're talking about height. So let's do 65 or 3 inches divided by 65. What will be the result? 3 divided by 65. Okay, I got 0.46, 0.5. Okay, what will be S divided by X bar? 7 divided by 175. .04. Okay, what about the very last one? 4 divided by 175. So S divided by X bar, that will be 0.22. So the first one, I got 0.05. So even though And then the first one I got 0.5, and then the second one 0.4, and then the very last one 0.22. So even though the middle one had the highest standard deviation, that doesn't mean that that has the highest. Should we use the most specific answer, or is rounding okay? For this time, rounding is okay. I just wanted to explain you that even though the standard deviation is larger, doesn't mean that that's like, doesn't mean that the variation is larger. It just means like the standard deviation is larger, but you are comparing different things. So that's leading us to the next topic will be Z-score. That way you can compare it a number on the graph. So this is the Z-score, measures of relative standing. So that way we are comparing measures between or within a data set. And it's called Z-score. So the Z-score basically the number of standard deviation a data value is away from the mean. We'll see what a Z-score means. So Z-score, we're gonna compare our data value to a point on this Z-score. So what we're gonna have as a Z-score, we're gonna give this a value. Because right now you only have 1 standard deviation, 2 standard deviations, and 3 standard deviations. And even though you got the standard deviation, which it could be 3, it could be 7, it could be 8, it doesn't mean like even though you have it doesn't mean we just proved that even though the data point was 7, the coefficient of variation was 0.4. So it was lower than the standard deviation that had 3, which it was smaller. So in order to get the Z-score, we're gonna need a value, an X minus our mean, let's see. And of course, we're gonna have 1 for our sample and then 1 of our population. So what's the mean for our sample? X bar, very good. And what will be the mean for our population? Mu, very good. And then what will be the symbol for standard deviation for a sample? Yes, very good. And for a population, use mu and sigma, very good, very good. So this is the formula to get to translate a data point to a Z-score. So let's do another example. So let's go back to our inches, and then we're gonna have our, so this is gonna be, now we're gonna talk about population, because our whole population will be the whole team of the dispersed team. And then let's say, I have 2 examples. So the first example will be measuring all the team's height for dispersed team. So the mean for dispersed, it's 71%. I mean, 71.5 inches. So let's do that. So let's see our Z-score. So can someone tell me what was the formula for Z-score? So we got a Z-score. This was for a population. So we're gonna have our data value, which is X minus minus the mean, which x bar, divided by standard deviation, divided by s. Very good. And then for sample, we got x, I mean z is equal to x minus what? Mu divided by sigma. Very good. So we got example 1. They're giving us the mean of the team, which is mu, and they're giving us the sigma. And we are gonna translate this data value to a z-score. That way we know where on the graph it. So a z-score is always x and then +1, -2, -1, -1, but it doesn't have the s over here. It's just a 1, it's just a 2. Aren't they the other way around? Yeah, you're right. So this will be for our population, and this will be for our sample. Yeah, got very smart students. Perfect. So our example 1, it will be about spurs. And they're telling us that Team Duncan is equal to 83. And then the mean will be mu equal to 71.5 inches. And then sigma 2.1. So I'm gonna let you guys do this one, and then I'll wait for the results. Or C score will be equal to, so we're gonna have 83 minus 71.15, and we're on this. Remember, whenever we did standard deviation, we square it, and then we take out the square root because we didn't want it to be either positive or negative. We just wanted to be the standard deviation. But for this one, we do want, it could be positive or negative or z-score. Yes, you're right. So over here, cool. So what's our z-score? 83 minus 71.5 divided by 2.1. So our z-score is 5.476. Okay. What about for example 2? Let's put Miami. So we got Shaquille O'Neal, 86 And then we got mu, 80. And then we got sigma, 320. Okay, so we got, now we can compare apples to apples because we convert them into a Z-score. So a Z-score will be a point in a graph. So if you have your Z-score, this is, you can have 1, 2, 3, 4. So 1 will be right here, 1.8, and then 5.5 will be way over here. So who's relative taller? So now that we have a number to compare, that we're comparing apples to apples, meaning Z-score, means that the higher the number, the higher, the taller it is. So yep, Tim Duncan will be, on this case, taller than the Miami Heat's Shaquille. I think that's all I got for today. I think I finished this time on time. And this will be, and there is a graph. I could, if you want, I could explain more on the Z-score, but basically that's what it means. Like it's translating your data into a point that will, like if you compare a Z-score to a Z-score, you're comparing apples to apples. So that way you could see the difference between one data point and the other data point. Yep, so this compares data values. That's exactly what it is. Now, on this case, you need an input. So in order to get a Z-score, you need a data value. So in this case, we decided to compare Tim Duncan and Shaquille O'Neal. So in this case, you are comparing a data point. And then on the other note, I got a confirmation on the workshop, on the 3D workshop, which I thought is really important because 3D, you use it in everything. You use it to model a can, you use it to model a pen, they use it to model characters, computers, cell phones, anything now, even landscaping or even construction. So I think this will be very useful. That way you could, I guess, get exposed to it, and then you decided if you like it or if you don't like it. That way I want you guys to get exposed to 3D. And since you're young, you could just start now. We're gonna give you some free tools and you could start becoming an expert at modeling. So our next Thursday class, I wanna give you like a background of what's 3D, what are all the softwares out there, and what technologies do they use, and what fields they use 3D, like engineers or for word testing or for fluids or for constructions, for creating characters, creating jewelry. So I want to explain to you a little bit more. And the workshop is going to be on Saturdays. I hope you guys can make it on Saturdays. I don't have the time yet. I'll have to confirm, but I'll keep you guys posted. And let me know if you have any questions. I'll stick around for a few minutes and enjoy the rest of your evening. Thank you. Thank you, guys.